We're continuing our study of logic in this next section, propositional equivalences. Alright, so these compound propositions we'll be looking at, they can be broken into three types. So the first type are called tautologies, and those are always true. Okay, so no matter what the internal propositions, say P, Q, and R are, they always turn out to be true. Contradictions, those are another type that are always false. Alright, so these are kind of special cases, these tautologies and contradictions. Most of the time, your compound propositions are going to be true or false. So here's a simple example of a tautology. So not P or P. So why is that a tautology? Well, so P is either true or false, so not P and P are going to have opposite truth values. One is true and one is false. And then the OR operation is true if one of these guys is true. So they're not both false. So false or false is false, but everything else is true. Okay, so this combination, it's always true. So it's a tautology in our new jargon. If we put an and between not P and P, well, that's always going to be false, right? That's a contradiction. For and, that's true when these are both true, but these are never both true. Okay, so that's a simple contradiction. How about this one? If you do P and P, well, that's going to be true. If P is true, it's going to be false. If P is false, so that can take both values. So that's the most common case, that's a contingency. Alright, so now we know what a tautology is. It's just something that's always true. Our second definition, two compound propositions P and Q are logically equivalent if this biconditional statement, P if and only if Q, is a tautology. Alright, so this is the idea of logical equivalence, and we have this notation. So P is logically equivalent to Q. Okay, and it just means that P and Q always have the same truth value. If P is true, then Q is true, if and only if. And if P is false, then Q is false, and vice versa. Alright, so we're using this symbol with three lines for equivalence. Yeah, it's like equality for numbers. So with this notation, tautologies are equivalent to T's, they're always true. Contradictions are equivalent to F's. So not P or P, that's equivalent to T. Not P and P, that's equivalent to F. Alright, so we're getting used to this new these new definitions and notation. Here's an example. Show that P implies Q and not P or Q are logically equivalent. Alright, so we'd like to show that no matter what P and Q are, these two expressions always have the same truth value. Alright, so if this guy is true, then this must be true. If this is true, then this is true. If this is false, then this is false. So they always, no matter what P and Q are, they're always supposed to have the same truth value. And maybe the simplest way to check is, just make a truth table. So as usual, here are the 4 combinations of P's and Q's. Here's not P, so switching the truth value of P to its negation. And then here's not P or Q. Okay, so not P or Q. That's only going to be false if not P and Q are both false. The rest of the time it's true. Okay, so not P or Q, we get T, F, T, T. And here's our P implies Q. Just from our definition, that's the same, so T, F, T, T. Okay, so P implies Q. It's only false when you have a true implying a false. That's the only time the implication is false. And that's the only time that not P or Q is false. Alright, so the fact we're getting the same columns here tells us that these two guys are logically equivalent. Okay, so in our notation we can write it like this. P implies Q is equivalent to not P or Q. So this is a useful formula we'll use later. Okay, so the idea of equivalence for propositions is similar to the idea of equality for numbers. And just like we have the rules or laws for arithmetic, we also have them for propositions. Okay, so you know that if you add or multiply two numbers, 2 plus 3 equals 3 plus 2, or 2 times 3 equals 3 times 2. The same is true for or and. Okay, so P or Q is logically equivalent to Q or P. And the same for and. Okay, so this, we're saying that or and are commutative operations. So you can switch the order. It doesn't matter. Okay, and you can see why that's true if you look at the truth tables. So on the truth tables, yeah, it doesn't matter which is the order. You're getting the same answers. Okay, then we had the idea of associativity. Okay, so we're not switching the order here. We're kind of timing the operations differently. So if you're using the or operation on 3 propositions, so it doesn't matter if you or the first 2 first, then the third, or if you or the second and third first and then the first, you'll get the same answer. Just like if you're adding 3 numbers, it doesn't matter if you add the first 2 or the last 2. And for multiplication, the same. And also the same for the and operation. Alright, so or and are both commutative and associative. So if you're anding a bunch of things together, you can drop the parentheses and just do the operations in any order. We'll also use that later. Okay, how about if we combine operations? All right, so this is similar, but we have P or Q and R. All right, so the way that works, yeah, this is like a distributive law for, say, multiplication over addition. So P or Q and R, it's equivalent to P or Q, parentheses, and P or R. Alright, so yeah, we definitely need the parentheses here. Alright, and it's the same with and. So P and Q or R is equivalent to P and Q or P and R. So yes, you should be thinking of distribution of multiplication over addition. So A times B plus C is equal to A times B plus A times C. So it's the same idea here. And again, you could check each of these using a big truth table with 8 rows. Okay, we're not going to check it. So an example in English. So let's look at this statement. So to board the plane, you must have a ticket and either a passport or a driver's license. Alright, so this is like a domestic flight. Alright, so we're So that's similar to this situation. So P is you have a ticket, and Q is you have a passport, or R is you have a driver's license. Okay, so it's like we have parentheses here. Okay, so to get on the plane you have to have a ticket and one of these two forms of ID. Okay, well that's supposed to be equivalent to this stuff. So to board the plane you must have a ticket and a passport. That's this situation. Or a ticket and a driver's license. Okay, so I hope you can see that, yeah, these are really saying the same thing. Okay, yeah, so there's only two ways to get on the plane. You have to have a passport. So you have to have a ticket, and then you can either have a passport or a driver's license. Okay, some more laws, this time involving negation. Okay, so remember the negation of a proposition is just it's not the case of the proposition. Okay, so there's not operation. Alright, so if you have a proposition and apply, so if you apply not, it just switches the truth values, and if you switch them again, you're back to the original. Okay, so not P is equivalent to P. Yeah, this might remind you of multiplying by -1, so minus negative of a number, you're back to the original number. Okay, and then it gets kind of interesting if you negate, let's say, P or Q. So not P or Q, is that equivalent to not P or not Q? Well, in fact, no, it's equivalent to not P and not Q. Alright, so to make it work, that if you're negating an or, it ends up as an and when you take away the parentheses. So yeah, so we need not P and not Q, but the operation changes, switches to an and. And the same thing here, if you're negating an and operation, you need an or on this side. Alright, so these are called the De Morgan laws, after this mathematician, logician. Alright, so yeah, these are not obvious, but we can check them using truth tables. So that's example 3. Check that not P or Q is equivalent to not P and not Q, using truth tables. Alright, so here's the tables. Yes, so first working out the left side. So P and Q, here's P or Q. And then here's the negation, just switching these T's to F's and F to T. Alright, so that's the left side, looks like this. And then working out the right side, yeah, first doing the nots. Not P and not Q. And then hit those with an and. And so these will all be false except for true and true, that's true. Okay, so we get each side. And we see that, yeah, they match. 3 F's and a T, 3 F's and a T. So these columns are the same, so that tells us that, yeah, these are logically equivalent. No matter what P and Q are, the left side, the truth of the left side is always equal to the truth of the right side. Alright, so what's an example of that in English? Suppose P says, I'll have pizza for dinner. Q says, I'll have a burger and fries for dinner. And so if you look at this statement, so P or Q says, I'll have pizza or a burger and fries for dinner. So what's the negation of this whole thing? So if it's not the case that I'll have pizza or a burger and fries for dinner, okay, so the negation is, according to De Morgan's law, it's not P and not Q. So if I'm not going to have pizza or a burger and fries, that's equivalent to I'll not have pizza and I'll not have a burger and fries for dinner. Okay, so we're starting with an or, but then if you negate this whole thing, you need an and. Alright, so yeah, you were going to have pizza or a burger and fries, but then you change your mind, you're not doing that. Okay, so that's equivalent to saying I'm not going to have a pizza and I'm not going to have a burger and fries. So that's an example of this logical equivalence. I hope it makes sense. Yeah, in the book there are a whole lot more of these equivalences. Okay, yeah, so again, yeah, we're just following this section. So tautologies, contradictions, contingencies. Tautology is always true, contradiction is always false. And two compound propositions are logically equivalent. That means that P, if and only if Q, is always true. Here are those laws we're looking at. And yeah, here's the check we looked at. Yeah, we did this one. Yeah, here's checking that distributive rule. So P or Q and R distributes to P or Q and P or R. And here's the checking. And so here's the left side, here's the right side. So the same T P's and F's. Okay, so these other equivalences I mentioned, so identity laws, if you and something with T, that's equivalent to the original, or if you or something with F. P or P is equivalent to P. P and P is equivalent to P. Those are easy to check. We saw this one. Not P is equivalent to P. Commutative laws, associative laws for or and. Distributive laws, De Morgan's laws. Here, some more cases, if instead of P, Q, and R, if two are the same, so P or P and Q, that's equivalent to P. The same the other way around. And we saw these two at the start. Some more here. We saw this one. So P implies Q is equivalent to not P or Q. And some more equivalences involving implications. Here for the biconditional, so P, if and only if Q is equivalent to P implies Q and Q implies P. That makes sense. You want the arrow going in both directions, from P to Q and Q to P. Alright, so some more equivalences there. And for the implications, so we saw last time that an implication P implies Q is equivalent to its contrapositive. That's not Q implies not P. So so this is an equivalence we saw earlier. These really mean the same thing. P implies Q and not Q implies not P. Okay, so just a couple more examples here. Example 4, use De Morgan's laws and the double negation law to show that not P implies Q is equivalent to P and not Q. De Morgan's laws just involve ors and ands and negations. So first we have to convert this implication to, in this case, an or. Okay, so using this relation equivalence we saw before. Okay, so so these are like, if you remember trig identities, or if you've seen them already in pre-calculus. So we want to show this identity. So the idea is start on the left side and kind of ignore the right side and just work with this side. Okay, so P implies Q. We're going to replace that with this first. There's still a not on the outside, so it's not this. So it's not P or Q. Q. And then we hit that with De Morgan's law. Okay, so not something or something is not the first thing and not the second thing. Alright, so this is De Morgan gets us to here. Okay, and now we have a double negation, so that just turns into a P. Okay, so this is equivalent to P and not Q. Alright, so did you see that? So that step here, so if you're negating an or, it turns into, if you're negating an or like this, it turns into an and of the two nots. Alright, so we got to the right hand side, so that proves the identity. This is equivalent to this, is equivalent to this, is equivalent to this, the target we were looking for. Okay, and one more. Use the laws to show that this compound proposition is a tautology. In other words, show that this is logically equivalent to T, something that's always true. Okay, so again, we want to convert this implication to an or using the so this is equivalent to not this or this. All right, then we want to negate this and. Okay, so using De Morgan's other law, we get not P or not Q. All right, so now we just have ors everywhere. Yeah, we know that or is associative, so that means it doesn't matter which of these ors you do first, so you could just write it with no parentheses. Okay, so it's not P or not Q or P or Q. We also know that or is commutative, so you can switch the orders. So let's put the P's together. Okay, so not P or P, or not Q or Q, put the Q's together. Okay, now we can choose to do or these first. Not P or P, that's always true. And not Q or Q, that's also always true. And true or true is equivalent to true. Alright, so that proves our compound proposition. Yeah, it is tautology. So yeah, we could have proved this using a truth table with 4 rows, but yeah, here we're just getting used to using these different laws. Okay, I think we've covered everything. Yeah, who was De Morgan? Yeah, Augustus De Morgan. Yeah, he worked on these basic logic operations. Yeah, he did a lot more as well, of course. Okay, so that's it for this section.